Okay, hey everybody, I'm going to try to go through this kinematics quiz as quickly as possible, but still explain things as thoroughly as possible. This is from Khan Academy. This adventurous cliff jumper keeps jumping off cliffs and asking questions. It's important to note that the positive direction is this way and the positive direction in X is that way. Which diagram best describes the velocity vectors and trajectory? The trajectory is just the path of this person during the person's fall. Okay, so as you look at our options for the velocity vectors, the velocity is, as a vector, is a magnitude and a direction, and it's not saying horizontal, it's not saying vertical, so that's the total combined, and that's really important. There are a lot of questions and they're asking about one or the other and sometimes a combination, so this is a combo. The trajectory is not in a straight line down. That is not how things fall. You fall more gradually at the beginning and then you pick up as you accelerate according to the square of the time. So we can rule this one out. This one looks promising. The vector at the very beginning is only horizontal. It's not yet kicked in that gravity is going downward. At the moment you start, you do have forward velocity. Then as the gravity pulls this person downward, their vertical component increases by the square of time. That makes sense. But meanwhile, the horizontal stays that same length as you were to break that down. So that looks very promising. If you look at the other ones, no, it can't be that. That's a constant horizontal. That's the total vector operating on that. Why would it be going down if it's only horizontal? This is the right sort of a direction, but the lengths do not vary, and it doesn't reflect the increasing magnitude of that vertical component. So it's more like if this is a hockey puck on a string and it's going around in a circle, that's the kind of thing you get. So it is definitely C. Next, we've got this like paper strip. In the original version, it is a paper strip, but this is a car leaking oil as it drives along the road. Same exact concept as a dot strip. So it's exactly the same as in a quiz with a paper strip. So what is happening with our approximate graph of the velocity? Velocity is the change in your position over your change in time. And you could say, well, that's your final distance minus your second distance minus your first distance, or your initial distance, and your time final minus your time initial, if you want to think of it that way. But this is really simple. The change in your distance with time is consistent. These dots are all evenly spaced. So pick some arbitrary point and call that your initial velocity. So it's very consistent. It's not changing. You're pulling that tape, you're dropping those drops of oil at a consistent rate. Then it speeds up, but then it also is consistent and it's faster. So at some stage, it's going to be faster, but also consistent along this zone in here. This is consistent, and then at the end, it's also consistent, but slower. So it's going to be somewhat less than the beginning, and it's going to be like this. And in between, if you make it smooth, if you make it jagged, that's not a huge deal. It's actually, in real life, it's really impossible to have sharp corners, so you could smooth that over. It would be nice to see these horizontal in 3 places, and then the transition between those two, okay? The car is actually slowing down, that is decelerating, all right? So then when we get to this part, what's the acceleration? Well, if you carry these down, you do not have to, but it's helpful. It's going to be a 0 acceleration here. And then you're going to have a, I need to carry that down here. You're going to have a positive acceleration here, and then it's going to go back down to 0 right here. Now you can do open circles and closed, but it's really not clear what's exactly happening. And indeed, in the real world, that can't happen. It would kill you if you had instantaneous acceleration. So if you smooth those over, that's okay too. And then this is a negative acceleration, so that's going to be down there, and then it's going to go back to 0. So you need to see something like that for the acceleration, all right? Then this last one is something that makes you think about this observer here at point A. If you're an observer and you're taking these distances, and those are negative distances, when you plug it in here or into this, you're going to have for your final distance a smaller negative number. And when you're subtracting a bigger negative number, because it's far away, that'll be plus, and that's a bigger number. So it'll give you a positive, and your time then will still be positive. So it turns out this is exactly the same as the other one. It's going to go over, it's going to go up, and then it's going to go down, and it's going to go over, and these will be straight again. Same exact thing. All right. Hope that wasn't too tricky. On to Apollo. Here we've got a golf ball being hit on the moon. We're told that the gravity on the moon's surface is -5 feet per second squared. So gravity on the moon -5 feet per second squared. We're hitting a golf ball at an initial velocity vector of 60 at an angle of 20 degrees. So a velocity is a strength and in a direction. So there's no other way to draw that. That's not saying it's broken down for you. You've got to break it down. So doing that then, this horizontal component that's sending the ball along the line, that, as we've done before, is the cosine of 20 degrees, then times 60. A lot of times you write 60 cosine of 20. And then the vertical component then is going to be 60 times the sine of 20 degrees. Okay? So if you get your calculator out and quickly get those amounts, turn that on, and you do cosine of 20, and then multiply that times 60, you get 56.4, we're going to call that. And then when we do sine of 20 times 60, we get 20.5 for the upward component. I'm going to write that here just because it's a little bit out of the way. We get an upward vector of 20.5. So we know that we're basically shooting this golf ball up in the air at that velocity. We know from V equals AT that when it goes up and then comes back down, it'll have the exact same velocity. So we know that we can find then, if our velocity is 20.5 and our acceleration of gravity on the moon is 5, that's going to tell us how long it takes for it in the air to come down with that velocity. So I divide both sides by 5, and I get 4.1 seconds for my time for the second half or the first half coming down. 4.1 coming down to get that velocity, and then 4.1 seconds going up to lose that velocity and get it to be a velocity of 0 at the top. All right, well, if I know that it's 4.1 seconds on the half, then I multiply it by 2, and I get 8.2 seconds for the total time aloft. Well, if my golf ball is traveling at 56.4 feet per second, horizontally, I just simply times this by that 56.4. And I'm going to just quickly divide by 5, and then I'm going to multiply it by 2, and then I'm going to multiply it by 56.4. So I've not chopped any decimals, but that's about 463 feet. 463 feet. Okay? So how far did the ball travel before hitting the moon's surface again? Show and describe your work. I would maybe take a little bit more time to get through, but that is the basic answer. Okay? With the extra credit, I'm actually going to keep the video short and not tell you exactly how to do it, but what I would do is the same thing as up above, but this is some mystery velocity. We do not know. We'll just call it V. And when I break that down, and I know that's 25 degrees, it's going to be the cosine of 25 times whatever V is. I'll put v out in front for that horizontal component. I'll do the same thing for the vertical component, and then I would match what I do up above, where I say, I don't know what my actual velocity is, but I know that when I get that velocity, it's going to be equal to AT, and I know that the acceleration of gravity on the moon is 5, and I don't know what t is, but I know that my velocity, my vertical velocity, will be that v times the sine of 25 degrees, okay? And then I can get an expression for the total time by dividing by 5 and dividing by 5, and then I can sub that in to my, I can multiply that by 2, times by 2, and then I can multiply that times my horizontal component like I did up here, and now I'm going to get my horizontal component also with a v in it, and this v times the other v will give me a v squared, but it'll all be numbers, and then I can solve for v that way. And once I get that, I can go back and calculate the distance that the golf ball travels, and that is how you do it. So on to 4. In this case, an archer shoots an arrow nearly straight up in the air. I put in an archer in the picture, and so the arrow goes up, comes down, thankfully misses him, and exactly 6 seconds later, the ball goes past the archer on the roof of the building. Okay, so that is giving away the symmetry of the problem, that if it takes 6 seconds to go up and go down, it takes 3 seconds to get to the very top. When t equals 3, the velocity at the very top is that vector. It's not going anywhere and in no direction. It is, for that instant, the velocity is 0, okay? So then on Earth, if we use gravity is -10 meters per second squared, you could use 9.8. Your answers will vary very slightly, but I know that if I'm falling for 3 seconds, again, the velocity is going to be AT. So if t is 3, velocity at 6 seconds on the way down from being at stopped at the top will be -10 times 3 is -30 meters per second. That's the velocity at 6 seconds. Well, we know that if that's the velocity what is the velocity there? V equals 0. At 6 seconds, V equals 30. I should be writing in the answers. So then at 0, at the moment it was shot, it has to have symmetrically that exact same velocity if we pay attention to our signs. It's downward as it goes past you. It's upwards as it is shot. Okay, so the pluses and the minuses are important. At what time does the arrow hit the ground? Okay, well, to hit the ground, to understand the time, we need to get the distances involved here. So I'm going to use d equals 1/2 AT squared. And I know that if something falls for 3 seconds, because it's gone from 3 seconds to 6 seconds, I know that the distance is going to be 1/2 -10 and then 3 squared. So that's going to be -5 times 9, and that's -45. So it's fallen 45 feet, or 45 meters, I'm in meters, be careful, it's in meters, to right there, and it's going to fall an additional 20 meters to right here. I can then work backwards and figure out the time that it takes to hit the ground, okay? So if something then is falling a total distance of 65 meters, and it's falling at 1/2 AT squared again, then I've got 65, and we can say, well, that's a -65 since it's fallen down, and I'm dividing by -5. That gives me t squared. That's 13 is what t squared is. So I take the square root of both sides, and I get t then equals the square root of 13. So I'll turn that on, do 13, raise it to the 0.5 power, or take the square root of it, same thing. I get 3.6, very close to 3.6 seconds. So at what time does the arrow hit the ground? That's 3.6 seconds from the top. I have to add another 3 seconds, 6.6 seconds, okay? Whoops, there we go, 6.6 seconds, because it's going to be that 3.6 seconds added on to 3 to go up to the top. Finally, what is the velocity at the time it hits the ground? Again, velocity is equal to AT, so the velocity is going to be equal to minus 10 times 6.6. So the velocity then at the moment it hits the ground is negative 60. Let's see, nope, that's 3.6, because the time is only the time falling down. I apologize. Is only the time falling down, and so that's negative 36 meters per second, okay? So that's the final answer there, all right? Final answer there for part D. All right, hope that helps a little bit.